I'm going to be talking about the benefits of model-based generalization and reinforcement learning. And this is joint work with Aditya Ramesh, Louis Kirsch, and Jürgen Schmidhuber. And this is based on our ICML paper from 2023. Okay, so there's this general impression that models should be more sample efficient, or model-based RL methods should be more sample efficient. But there's like relatively little work actually clearly explaining why this should be the case. So that's kind of the question I'm trying to address in this talk. And there's also like a body of work arguing that if what we ultimately care about is like the value function of policy, then maybe we're better off just learning the best value function of policy we can from the data, rather than introducing like this intermediate kind of potentially noisy step of learning a model when we don't really care about it. So the first thing I wanted to mention is that like a lot of the most obvious benefits people sometimes associate with model-based learning are actually shared with experience replay. So in particular, if you consider a Q-learning agent trained on the following simple grid world with and without experience replay. So this is just the agents trying to get from the start state S to the goal state G. And then I'm just visualizing the greedy policy partway through the second episode. So if you don't use experience replay, in other words, if you're just updating from each transition at the time you experience it, then the only non-trivial transition you basically observed in the whole first episode was on that step to the goal. You assume like getting to the goal has a reward of 1 and the reward everywhere else is just 0. So if you don't use experience replay, the only like place where the agent's actually updated its greedy policy is on that last step. And this is in spite of the fact that it's already like spent all this time wandering around the whole environment and gathered all this data on like the layout of the grid in general, but all that experience is essentially wasted. So on the other hand, if you actually use experience replay, you can replay that experience in a different order than you observed it. And by doing so, you can propagate value kind of throughout the state space. And you can achieve this either with experience replay, but you can also achieve it with like a learned model, which lets you essentially like imagine transitions other than the one you're actually experiencing. Whereas experience replay just replays transition from the past. So experience replay can essentially be seen as like the simplest possible kind of model. And already captures that kind of benefit. So given that experience replay is so simple and effective, is there really any additional benefit to learning a parametric model? So one argument is that a parametric model that generalizes can generate imagined experience that doesn't explicitly appear in the data set. And if that model basically generalizes well, then we can imagine that an agent using that additional experience to learn a policy can learn a better policy than it could without it. But parametric value functions also generalize unseen states and actions within a model-free approach. So then the natural question becomes, why is model-based generalization better than value function generalization? It's not sufficient just to say that models generalize because they both generalize. So why is it better to like imagine like the next state following a transition we've never seen before than it is just a letter value function, like estimate the value of that, say, state action pair we've never seen before? So that's the question I'm going to be addressing, and I'm going to start with like a theoretical motivation for why that might be the case. And then the second half will also show some experiments illustrating the kind of like the intuition behind the theory also is relevant in practice. Okay, awesome. Hopefully everything's good now. So yeah, we're assuming basically the transition function belongs to some known hypothesis class and the reward function is known. So, and then now we're going to assume that the agent gets some data set of state action to next state transitions. And we basically want to use this data set to somehow prune down the set of possible optimal action value functions. So the initial set of possible optimal action value functions in this case is just going to be optimal action value functions of the initial model class. Because basically, remember I said the agent assumes they know the transition function belongs to some class. So for each transition function in the class, there's going to be some like optimal action value function that you can in principle compute, given that you know that's the transition function and you know the reward. So I'm just saying here before the agent observes any data, all it knows is that the optimal action value function is going to be the optimal action value function associated with some model in that class. And then what we want to do is use the data set to somehow prune down that set to a smaller set of possible value functions that are in some sense consistent with the data. So that's the goal in this sort of abstract setting. So yeah, I'm going to now describe two different ways of pruning down the set of possible value functions based on the data that I'll associate with kind of the model-based approach and the model-free approach. So first of all, the model-based approach. So in this case, we're going to first use the data set to prune the set of possible transition functions. So we begin just by knowing the transition function lies in this particular model class. And then we're going to observe the data. And the way we're going to do this is basically, if you imagine that T of SA is the next state predicted by a particular transition function in our class when we take action A. And then if we have a transition SA goes to S prime in the data set, and T of SA is not equal to S prime, then we can immediately rule out T. And this is where it becomes important that I'm considering like the deterministic case, because that makes this very simple. If we observe a single sample that doesn't agree in the data set that doesn't agree with one of the models, we know that model is wrong. So if you were considering the stochastic case, this would be more complicated. You'd have to like gather statistics on each like transition function and see if it was like, we could rule it out with high probability. But here we can just observe one incorrect sample and know that that model must be wrong. And then at the end, remember what we care about is like the value functions, not the model. So as a final step, we're just going to consider the pruned set of optimal action value functions to be the set of optimal action value functions of the remaining possible models after we prune them based on the data in this way. So if you want to draw an analogy to kind of like the more typical model-based RL setting, you can imagine you're learning like an over-parameterized neural network, and you just train it to convergence on a fixed data set. And in this case, it's an over-parameterized neural network, say, transition model. So what you're going to end up with is basically a transition model that agrees with the data precisely or close to it if you train it to convergence on a fixed data set, but you don't know how it's going to generalize to transitions that you haven't seen. So that's like saying you don't know which particular function in that model class that's consistent with the data you're converging to, but you know you're going to arrive at one of them. And then after that, you just consider the set of like the action value function associated with that. Okay. So the next approach to pruning the set of possible value functions is the model-free approach. And in this case, we don't directly consider this class of models at all. We just want to work directly in value function space. But we do start by knowing that the optimal action value function is one of the optimal action value functions of these initial models. So that's the way that I'm kind of encoding the idea that we want our model-free approach to start with the same kind of prior knowledge as the model-based approach. But the way in which it prunes the value functions based on the data is going to be different. So yeah, basically in this case, rather than considering transition dynamics directly, we just want to prune value functions directly based on the Bellman optimality equation. So that's the Bellman optimality equation for this deterministic case. So there's no expectation in it since everything's deterministic. But basically all it says is that for the optimal action value function, it's the case that the optimal action value function is equal to the like immediate reward we get plus the optimal action value function of the best action in the next state. And the important thing is we know that this actually does hold for the true optimal action value function, at least for every transition that occurs under the true model. So we can use this as a valid way to prune possible value functions. So now if a particular state action next state tuple exists in the data set, then we can rule out every Q that essentially does not obey the Bellman optimality equation for that transition. And then this results in a set of remaining possible optimal action value functions that do obey the Bellman optimality equation for every transition in the data set. And if you want to draw an analogy to like what this would look like in a practical setting, this is basically like running Q-learning to convergence, again, with like an over-parameterized neural network on a fixed data set. So by doing that, you're going to basically end up with a value function that obeys the Bellman optimality equation for every transition that occurs in the data set, but you don't know how it's going to generalize to state action pairs outside the data set, which again is basically like saying you don't know which specific value function in this set of value functions consistent with the data you're going to converge to. Okay, so yeah, that's it for the abstract setting. So now I'm going to describe the main sort of theoretical result I want to convey in this talk. So here on the left, we have model space, and on the right, we have essentially action value function space. And basically, yeah, this picture just shows on the left side, we start with this initial model class. And then on the action value function side, we start with knowing that the optimal action value function is the optimal action value function of some model in that initial class. And then I'm just showing these two different ways I've described of pruning the possible data. So in the model-based approach, we first prune down the models that are consistent with the data, and then look at the value functions of those models. And in the model-free approach, we just work directly in the action value function space and consider value functions that satisfy Bellman optimality with respect to the data. And the key result here is that we can narrow down the set of possible value functions more in general by first pruning the set of models than by only enforcing Bellman optimality on a limited data set. So that's the overall main result. And another interesting thing is that for a tabular model class, so tabular here means basically includes every possible function from states and actions to next states. So in other words, your model essentially doesn't generalize at all. When you observe a particular state action next state tuple, it only tells you like the next state following that particular state action pair, but tells you absolutely nothing about any other state action pair in the space. So if you're basically, if your model doesn't generalize, if you're just dealing with a tabular model, then these two results are actually the same. So that blue circle with the model-based result and that sort of pink circle with the model-free result are actually going to be the same size. So to actually get a benefit here, you need some additional structure on your model class, basically. So your model needs to be able to generalize, but if it does, then there's your model-based result is will in general get you a smaller set.
Could you give? Oh, okay. Is this?
Sorry.
So yeah, I was just asking for some information why the blue is smaller. Like, why is it a subset of the pink?
Yeah, so I think that I'll probably be giving it tuition in like the subsequent slide. So you can ask again though at the end of like the theoretical section. It's still not clear maybe. Okay. Okay, so just to state that result a little more formally, basically the formal result is we consider a class of deterministic episodic MDPs with fixed reward function and transition belonging to some known hypothesis class. Then we have these three things that are true. So so HM of D here is basically the model-based set I described. So they're both sort of sets of value functions, but HM of D is the model-based one for a particular data set D. HB of D is the model-free one, so B here is standing for Bellman, and again of the same data set D. And what the first point is saying is that the model-based result is always either a subset or equal to the model-free result. So the model-free result can essentially never be better. Number two says that there are some choices of MDP class M and data set D such that the model-based result is actually a strict subset of model-free. So it is possible for the model-based result to be better, essentially, in the sense that it's a smaller kind of set around the true value function. And then lastly, for a tabular transition function class, so again, one that includes every possible mapping from state action pairs to next states, it's true that the two sets are actually exactly the same. And also the model-based result can be smaller by an arbitrary factor in some cases. Okay, so points 1 and 3 here are fairly straightforward proofs. So you can maybe look at the paper for the details there. And point 2 is more interesting, and it just requires us to show like a single example where it's true. So that's what I'm going to do next. Yes, Griffin.
So the first and the second and third point seem slightly contradictory, right? The third point and the star, because you're saying that in some case the HMD is exactly the same as HBD.
Yeah.
And you're also saying that HMD can be smaller by an arbitrary factor.
So there are
have to be the non-tabular case, right?
Yeah, it has to be in the non-tabular.
And so what is the thing that you need to make it as small as you want?
Oh, I guess I'm going to describe a problem that has this characteristic next. So maybe that will make it more clear. Yeah. Okay. Yeah. I see. Yeah. For the second point, we just have to show a particular instance where this is true. So it's obviously not true in all instances because, as Roshan mentioned, like for the tabular case, they're actually equal, but there are some cases where it is possible.
Sean has a question.
Oh, in the chat?
Yeah. Well, it's online. Yeah.
Oh, yeah.
You hear me? Yeah, so I'm wondering whether this is a fair comparison, because when you're saying that the model class or the model-based method can win, then you start to make assumptions about that. Oh, the model class actually contains the true model, but it's smaller than all possible models. It's not the tabular case when the win happens, right? But it's just you keep the model, like you could consider models for Q functions as well, right? Like, and so then you could say that, oh, if I have models for the Q functions, I don't consider all Q functions.
I am actually not considering all Q functions here, though. Because I'm encoding that I'm only considering the Q functions of the models. No.
Yeah, but okay, so when you're thinking about the Bellman consistency, that's a minimum set of constraints, but you could go beyond that because you're already using the Bellman consistency with the model class as well, or the model-based approach as well. So you could say that, oh, let's just consider linear functions or some other restriction on the Q functions. And then suddenly you would be able to produce examples where the model-free approach should be doing better than the model-based approach. Isn't that the case? It just depends on whether your modeling assumptions are right for the instance that you're considering. And if they are right, then like you can win with either the model-free or the model-based approach.
So my intuition for that is that if you have some restriction on your value function and you're assuming like a fixed state space, you basically could derive an analogous restriction on your model class from the value function, because the model class is in some sense more primitive. So this is just saying that like prior knowledge being equal, where I mean prior knowledge of some fact about the world, meaning the transition model in this case. The model-based
Can't I do that? Yeah, like can't I do that in the other direction too? So if you give me a model class, then I can eliminate all the Q functions or the Q star functions, which are not compatible with at least one of the models in the model class. And then suddenly model free result will look the same, right? Like I'm going to eliminate as fast with my model, so-called model free method than with the model based method, right?
Yeah, so I don't know if I have a good answer for that right now. I mean, there's a lot of cases that this result definitely doesn't cover, but maybe I can like explain in more detail what I think this does cover. And then after that point, maybe you can ask the question again, like with that new information in mind, if it's still an issue.
Sure. Okay.
Would that be okay? Okay,
Yep.
Thank you. Okay, so yeah, for point 2, we basically just have to show some specific instance where the model-based result is actually a subset of the model-free result. So that's what I'm going to do in the next few slides. Okay, so this is basically an example of an environment class where the model-based approach is clearly better in the sense I've described. So it results in a smaller set of possible optimal action value functions. And essentially the environment here has a known binary tree structure. So every like class instance has this structure where it starts in the root node, and then at each node, it's going to select either the left or right action, which will take it to the next node down in the tree. And then it'll just eventually go to the bottom. And essentially the state representations here are recording the current level in the tree as well as the action L or R taken to get to that point. So it starts in the root node with this 3, meaning like a countdown determination. And XX, which are just like sort of filler values because they haven't taken any actions yet. And then if it takes the action R, say, it'll descend to like this next node, which is 2RX. So it's now taking the action R, and it's like 2 steps away from termination. And then the environments in this class differ only in an unknown passcode. So it's basically a sequence of left or right actions. And then on the step before termination, essentially each correct letter in that passcode transforms into a 1. And each incorrect letter transforms into a 0. So the agent's also getting this sort of extra information saying that like which specific letters in that passcode were correct and which specific letters were incorrect. And the reward is basically going to be 1 if all digits are 1 in the final step, meaning that every digit of the passcode was actually correct for the specific environment instance, and otherwise it's going to be 0. So this is essentially just like a combination log problem where the agent has to enter a specific sequence of actions to get a positive reward. And if it enters any action incorrectly, then it's going to get a reward of 0. So the only difference is in this case, it also gets this sort of additional kind of dense feedback about like which digits in its passcode were correct. Okay, so now I just want to step through what the actual model-based approach I described and the model-free approach I described do in this case. So basically, I'm going to start with the model-based approach, and before observing any data, there's 4 possible transition functions in the class corresponding to 4 possible passcodes. So in this case, there's like a 1-to-1 correspondence between the passcodes and the transition dynamics for this specific model class. So I can just talk about them interchangeably. And now if we imagine like observing a single trajectory data set, so just always taking the right action and going down one particular path in that tree, then the data set looks like that. And then I'm just going to step through each state in this data set and then say whether we can prune any passcode using this model-based approach. So this first transition holds for every class instance, so we can't prune anything based on this observation. And the reason is essentially just because this is a fixed part of like the environment dynamics. It always goes from 3XX, takes the action R. If it takes the action R, it will arrive in 2RX. That holds for every model in the class. So we can't eliminate any transition functions from that alone. Same is true for this second transition. So still we can't prune anything. But then this third transition obviously does not hold for every model in the class. In particular, I said that on correct transitions, the associated passcode digit becomes 1. The transition on this specific transition, the correct digits in the passcode all become 1 and the incorrect all become 0. So this transition can basically only occur in the case where the true passcode is LR, because this is essentially telling us that the first digit in our passcode, which was R, was incorrect, and the second digit was correct. So naturally, the correct passcode must just be LR, where the first digit is flipped. And then the optimal action value function just has to be the one where corresponding to that same passcode. So there's also one-to-one correspondence between optimal action value functions, transition functions, and passcodes here. And yeah, again, this last transition also holds for every transition function in the class because it's just going from, yeah, it always terminates after, I mentioned the black box means like the terminal state. I don't know if I said that. So it always terminates after like the step with index 0. So yeah, that's not telling us any additional information, but we've already narrowed it down to one possible passcode anyway. So there's no more information it can tell us. Okay, so now stepping through the model-free approach. So yeah, remember in the model-free approach, I said, rather than creating transition functions based on, yes.
But why is the last row of circles the last thing? Like, there is no action in there, right?
Oh, so it's the meaning is that all actions just follow the same transition there. So the actions are only relevant in like the tree part of the MDP, and then like in those last two steps, you can take action L or action R. It doesn't change anything. That's the idea. Is that potentially a question?
So you do take an action.
Yeah, I mean, you could assume like the action set changed. It wouldn't really change anything about the setup, but I'm just assuming like the agent takes the same set of actions in every state, and then in some states it just doesn't do anything. So yeah, so basically in this model-free approach, rather than pruning transition functions based on D, we're only going to demand that Bellman optimality hold for each of these transitions. And in this case, the initial hypothesis class corresponds to the optimal action value functions for each model in the MDP class. So yeah, basically this is something important to emphasize. I'm not just assuming like any value function could be correct as long as it obeys these Bellman optimality equations. I'm just assuming that we're going to use these Bellman optimality equations to rule out value functions that are not possible based on the data. But the initial set of value functions I'm considering is only those that are the value functions of some model in that initial class. So this is the sense in which I'm enforcing that the two approaches begin with the same prior knowledge. And maybe you could agree or disagree with this, but I think it's a valid way of saying like somehow we've encoded kind of the same world knowledge in our value function that we've encoded in the model. So that's the way in which I'm kind of enforcing that they begin with the same prior knowledge, basically. So yeah, it's not that we're considering any value function as long as it obeys these Bellman equations. We're only considering the set of value functions that are possible under some model in the class, and then we're using these Bellman optimality equations to prune out the ones that are not possible given the data. Okay, so if we do this, and then we step through what we can prune based on each transition in this set of Bellman equations. So basically the first one, just like it held for every model in the class, it actually holds for every value function in the class. So we can't prune any value functions based on this Bellman optimality equation. I should mention I filled in all the rewards with 0 here because the rewards are 0 for every transition in this set. So, and this actually follows from the fact that it holds for every model this transition holds for every model in the class, that the Bellman optimality equation must be obeyed by every value function in the class. But we can also show it explicitly. So to do that, you can just say that like, okay, basically there's two possibilities for the value functions we're considering. Either it's the value function where C1, so the first digit of the passcode was R, in which case this Bellman optimality equation just reduces to 1 equals 0 plus 1. And that's because like, if we're assuming the action we took was optimal, then it had an action value of 1 because we can reach the reward after taking that action. And naturally, like the next state we arrive at, the value is also 1 because there's some action that will still lead to the reward just because of the tree structure. So if the first digit of the passcode really was R, then yes, this holds. On the other hand, if the first digit of the passcode was L, then this just reduces to 0 equals 0 plus 0, because basically like we already took an incorrect action, so the value of that action has to be 0. And the value of the next state we arrive at, the best action the next state we arrive at is also 0. So it also holds in the case where the first digit of the passcode is L instead. So in either case, this Bellman optimality equation is obeyed. And the same reasoning basically applies that this holds, this next Bellman optimality equation holds for every value function in the class. So again, no pruning is possible based on that. But now based on this third Bellman optimality equation, we can actually start to prune something because this doesn't hold for every value function in the class. So it's actually is true for every value function in the class that the action value of this state action pair, so Q001 comma A prime, where A prime is anything, is always going to be 0 because we only get a reward essentially in that final transition if we're in the state 0, 1, 1. So only if we're in that state indicating that each digit of our passcode is correct do we get a reward. So naturally for every other state, for every model in this class we're considering, this action value is 0. So we can reduce this equation overall for every model in the class to Q1 of RR comma R equals 0. And that does tell us something. That basically rules out the case where the passcode actually was RR. Because if the passcode was actually RR, then the action value of this particular state action pair would have been 1. So we've now ruled out something. But look, the interesting thing is we have not ruled out as much as we ruled out in the model-based case on this same transition. Because like, based on this Bellman optimality equation alone, any other passcode is possible, just not that one. This would be true if the passcode was anything other than RR essentially. So we've only managed to rule out one possible passcode or one possible value function in this case. And once again, this last Bellman optimality equation actually holds for every model in the class. Because basically the action value of in the last step of anything besides like 0, 1, 1 is going to be 0. So for every model in the class, that will hold. Okay. So overall, the model-based result here is smaller than the model-free result. In particular, given the same data, the model-based result managed to prune all but the value function corresponding to this one passcode LR. And the model-free result only managed to prune this one passcode RR, leaving a set of 3 possible passcodes. And then if we move to a depth N tree, essentially the model-based approach is always going to prune all but one possible value function. And the model-free approach, unless we happen to get lucky and find the optimal trajectory on the first shot, it's going to leave 2 to the n minus 1 possible value functions. Yeah, basically, so all but 1. And yeah, so like what's going on here in general? Basically, the intuition is that the model-based approach, because it's dealing specifically in the space of transition dynamics, it can actually make use of this extra information we know about like the dynamics, which is that in that last step, we actually get that information about the correctness of each individual digit in our passcode. So it's able to make use of that to rule out more possible value functions. Whereas the model-free approach is only reasoning in the space of value functions and only based on Bellman optimality. So it doesn't see like, in some sense, which specific state we arrived at. It just sees that we arrived at a state with value 0. Or another way to put that is it basically is only using information that's relevant for predicting the value of the current state, but it's not going to be able to capitalize on this information that's useful for predicting the value of other states, which is this dense feedback we get about like the correctness of each digit in our passcode. Yes.
So this only works because it's a binary tree, right? If you split it into 3 options.
So this specific example, yes, but I mean, you could come up with other examples where the model-based approach still has more information, but that is like the mechanism that's making it work here. Yes. Yeah. I think if you had like a trinary tree, it would probably just, or like like 3 digits, it would narrow it down. You could still say probably the model-based result was smaller, but it wouldn't like narrow it down to one possibility, right? It might narrow it down to a larger set of possibilities. I would think. I haven't thought about it. Was there other questions?
Okay.
Yes.
Since I'm trying to rule out like what is not the optimal trajectory, would this be harder in the model-free version if I have to learn the reward?
So it depends what you mean by learning the reward. I guess if you allow like all possible rewards, it might be harder. But if you also assume you have some like information about the reward, I think you could still like similar examples, even where the reward function is unknown initially.
If the reward is 0, 1.
Yeah, sure.
I would still be able to rule out one passcode.
Yeah, so I guess if you don't assume you know anything else about the rewards, then yeah, it might make it harder. But
then I would have the same complexity also in the model-based case, because you give me, I don't know, the 0, 1, 1, and which is whatever, like the result of the matching with the class code, and then I would have to learn the reward, which give me the same complexity as the model tree case.
Yes, so it's possible. There's definitely going to be examples where they're the same. In particular, like the tabular case, for sure they're the same. And there's probably, I mean, I know there's other examples that aren't tabular, but where there's this complexity is still the same. But I'm thinking it would just depend on like how hard it is to learn the reward in the general case, right? But I don't think like learning the reward is going to fundamentally break the logic here. That would be my thinking. But maybe in the specific example you're discussing, like it would kind of invalidate this specific example. I'm not sure off the top of my head. Yes.
Shava, if you want to go ahead with your question.
Yeah. So thanks, Kenny. I understand now what I was confused about, and this is great. One like maybe a follow-up to the previous thought is that maybe what's going on is that if you consider all possible reward functions simultaneously with the model, so-called model-free approach, then it would gain back the strengths of what you call the model-based approach. So
Yeah,
right?
I think that's true. That's kind of like a frequency representation of your environment almost, as opposed to
Right.
like a time-based environment.
It's like the reward-free learning plus model-free is kind of like implicitly thinking about the models anyways. Yeah.
Yes, so that I would agree with, I think.
Okay, good. Thanks.
Okay, so yeah, so this example is obviously like highly contrived to just clearly illustrate how a model can capitalize on value relevant information that a model-free method doesn't. But it's easy to come up with like practical examples where this should also hold intuitively. So basically, you can imagine learning the rules of chess from relatively few games, given sort of a model class with reasonable generalization properties. And then having learned those rules, we can in principle work out how to play optimally without observing any more games. So for example, if we run like AlphaZero by self-play, using that learned model. And what this previous result suggests is that in cases like this, we probably cannot get the same benefit with a model-free method, even if we somehow manage to encode like the same generalization properties into the value function that let us like generalize and find the rules of the game fairly efficiently. So there's something fundamentally like limiting about just doing updates in this sort of temporal difference Bellman optimality way. But yeah, as Shava mentioned, like if you were learning all possible reward functions, that might change the situation, probably would change the situation. So yeah, with that said, there's definitely, so I think this result is interesting and sort of like intuitively useful, but there's definitely some key assumptions and limitations around it. So the first is that I'm assuming the model and value function class have the same prior knowledge of the environment. And specifically, I'm enforcing that by saying that the initial value function class we're considering is just going to be the optimal action value functions of the models in that initial class. So this is clearly not going to be true in practice. Like if you're using neural networks, then whatever like generalization characteristics or inductive biases they have are pretty nebulous, and they're not going to be the same between like a model and a value function. But nonetheless, I think this case is interesting to look at because it's basically saying like, if we somehow manage to work out these properties of the world that are really useful for like making good machine learning algorithms or reinforcement learning algorithms, then in general, like we're better off using those properties in, I think, a model-based algorithm than sort of like a model-free algorithm, at least in like the sort of model-free algorithm meaning like the temporal difference approach that I basically described previously. And yeah, the second is that the true model is actually contained in the function class we consider. So if we're in this situation, so this has been usually called realizability, like if we were in this situation where the true model is outside the function class we're considering, then we want to do something like finding the best possible model in that initial function class. And like if we're in that situation, then you might still get a generalization benefit from working in the space of models. But that's going to be somewhat offset as you get more and more data. And the logic there is because if you have like an unlimited amount of data, at some point your data set is just going to be a better empirical model of the environment than the best model you can represent in that limited class. And at that point, you're better off just fitting the best value function you can to that like large data set, because the value function is closer to what you actually care about in the model. And if you learn the best model you can as an intermediate step, that's just introducing another step of error propagation. So yeah, this result is kind of dependent on the true model being in your function class. And then lastly, I'm assuming that the value functions of learned models can be exactly computed, and I'm ignoring the computational expense of doing so. This is also not true in practice. Like in practice, just learning the value function given like specific model is going to be like computationally intensive and potentially error prone in itself. So yeah, basically overall what I've shown here is some particular limit in which it's clear that in a sense, like the model-free approaches have a benefit, or sorry, model-based approaches have a benefit, but this in practice, there's going to be a lot of other considerations you should take into account if you're deciding whether to use like a model-based or model-free approach. Yes.
So here you haven't mentioned that like the transition dynamics were assumed to be deterministic, right? So
Yeah.
are you saying that if they were stochastic, you would have a similar reduction in complexity, like we will?
So I think so, yes, but it's a lot like, okay, I think the same intuition applies, but like actually designing like a simple sort of intuitive setup like this would be a lot harder. Like I've thought about it a bit, and the natural thing would be kind of like some kind of Bayesian setup maybe, because this is sort of like Bayesian, you're just dealing with sets. But it's pretty hard to even like define like Bayesian Q learning in a setting that's satisfying, in a way that's satisfying. Because like, what does it mean to like consider the set of things that sort of, I don't know, like probabilistically obey your Bell-Mathematic equation? It's just like hard to define. So it becomes a lot more finicky, but like, I personally think the intuition is still useful, but to actually like show some similar result might be more complicated by a wide margin. Yeah. Okay, so overall, what does this result say? Basically modulo all the like limitations I mentioned in the previous slide and the one Abhishek just brought up. This is assuming we basically successfully design a model architecture with favorable generalization properties for a problem class of interest, or in other words, if we like have some properties of the world that we know are useful for building like good model-based approaches, then a model-based approach using this architecture is going to provide a sample efficiency benefit, which we can't recover just by like encoding analogous generalization properties in a value function and then training it with sort of model-free temporal difference methods like the ones I've described. So what doesn't this result say? Basically, it says nothing about the performance of like an arbitrary model or value function on a single specific problem instance. And in particular, like you have a single problem instance, your best value function is obviously just like the true value function of that problem instance, and then you don't have to learn anything. So that's great. So it's not saying that it's going to be better in every case if we're allowing for arbitrary models and value functions. And it may well be the case that, yeah, a certain value function is a better fit to a particular problem than a specific model class. So it's saying like, given the same sort of inductive biases, your model-based approach is likely going to have a benefit, but it's telling you nothing about what the right inductive biases are. So yeah, who knows what happens in practice. Okay, so that's it for sort of the theoretical motivation. And yeah, if there's any other questions now, I guess now would be a good time. Yeah.
In the stochastics dynamic setting, do you think the theory will also translate, or do you think it's just gonna depend on the environments?
So I think some version of this would go through, but I don't know what it will look like basically, because it's definitely more complicated. So this is nice because it really, I think it follows very intuitively in this case, and in like the stochastic setting, it just introduces a lot more complexity.
Yeah,
so
I guess like there's some question about in the stochastic case, when you do dynamic model learning, you also start learning the dimension. Like it's going to be with respect to the dimension of the state too. So if let's say you're learning dynamic model of the images, then
yeah,
that's like a way more difficult estimation problem than just an indicator function saying yes.
Yeah, that's definitely true. Yeah. So and the other thing is it becomes a little finicky to like say what you mean by Q learning, I guess, in that setting. If you're reasoning kind of probabilistically about things, like Q learning is not in itself like it doesn't naturally translate into sort of an algorithm where you're reasoning about sort of sets of value functions, I guess. So it becomes a little harder because like I was talking in terms of like sets of value functions here, but if you have stochasticity, then it's not clear how you would use sort of a Q learning style rule to narrow down like a probability distribution over possible value functions or something, I guess. So that's another complexity, but yeah. So I think something similar, like similar intuition anyway should apply, but I don't exactly know what the right way to formulate it is. So anything else? Okay, I'll carry on then. Okay, so this section is kind of trying to show how the intuition behind this might translate into practice. So I'm going to start with just sort of a simple illustrative environment, which shows like an empirical benefit to model-based learning. So the idea here is that we're going to train model-based and model-free algorithms on 4 fixed data sets with varying levels of coverage of the environment dynamics. So this is still different from like the sort of online RL setting because I'm using fixed data sets. And the environment in this case is just this 3x3 grid world with sort of arbitrary placements of walls. And yeah, again, I'm going to try 4 different data sets in this case, with the idea being that I want to see how the model-based and model-free approaches are able to generalize based on that limited data. And all the data sets are going to include these basic configurations in which there's basically only one wall, and I'm going to include every possible transition in those configurations. So all that data is available in all the data sets. And then ultimately, I'm interested in, say, these configurations with 2 walls, but I'm only going to provide the agent with like a limited amount of data about those 2 walls configurations. So the specific data sets are differentiated by how much data they include about those from those evaluation configurations. So the most generous one is like all evaluations. So it just also includes every transition from in that evaluation cases. And then beyond that, there's path to goal, where I include like only the optimal actions in those 2 wall configurations. And there's single cell, where I only include the action that's like furthest away, or sorry, I only include the state that's furthest away from the goal, but I include all the possible actions in that state. And then last of all is the no evaluation case, where I don't include any evaluation data at all, but I still include all the data from the basic configurations. So all the data sets again include those basic 1 wall configurations, but vary in how much data they include about the 2 wall configurations. Okay, so now we're going to see how a model-free and a model-based approach do using each of these sort of levels of data coverage. So for the model-free approach, I'm just using sort of DQN, but trained directly on that fixed data set. So pretty straightforward. And then for the model-based approach, I'm using a feed-forward neural network model with Bernoulli outputs, and then trained on that data set. And then I'm going to use that model essentially to generate imagined transitions to learn a value function. So by Bernoulli outputs here, I mean basically like the state representation here is just a big vector of 1s and 0s. So in particular, like it's going to have a 1 for each wall, so you know where the walls are in that particular state. And it's also going to have another 1 indicating the location of the agent. So it's kind of like a 1-hot representation. And then, yeah, so that's the model. And then that's the input to the model. And the model is going to predict essentially like a vector of numbers between 1 and 0, which represents like the probability of that digit being active in the next state. So in general, this kind of model is not going to be good enough to represent arbitrary stochastic dynamics. But since I'm considering like deterministic environments, it is good enough to represent the transition dynamics in this case. So then I'm going to consider basically, yes.
So you use neural networks to over-parameterize both the value function and the model, or
That's the idea, yeah. Yeah. I mean, I don't know whether I succeeded at over-parameterizing it, but it has like quite a few parameters, yeah. So yeah, and then there's basically 2 different model-based agents I'm trying, but only different. The model learning procedure is the same, but they differ in how they're using the model to generate data for training DQN. So the 1-step model is just going to train DQN on 1-step rollouts that are initialized from states in the data set. So we take some state in the data set, have the model predict the next state, and then use that as a training example for DQN. And the 10-step rollout case is the same as the above, but now we roll out the model from states in the data set 10 steps into the future instead of just 1. So generate a state, feed that state back in the model, and generate the next state that comes after that, essentially. And the reason for testing these 2 things is, again, like in the theory part, I sort of said, like I was assuming you can just naturally or automatically come up with the value function that's associated with a given model. In practice, we can't do that. And like a common approach would be to generate rollouts from states in the data set I'm doing here. If you make those rollouts sort of infinitely long and have enough of them, then in principle, eventually you would kind of get the true value function of that model, but we don't do that in practice. So I just wanted to get a sense of like, how much does it matter that we do longer rollouts versus say just 1-step rollouts?
Oh, question. Is
Yes.
the n-step rollout using like n-step return, like n-step?
So no, it's just using the model to in this way to generate transitions.
Oh, and you just
But it's always DQN trained on like single step returns essentially.
Okay.
Yeah. That make sense?
Yeah.
Okay, awesome. Okay, so now I'm going to show the results. So essentially, if we have all evaluation data, so basically every single transition that can occur in the evaluation configurations, then all these approaches succeed. And what I'm actually showing here is the color illustrates like how many out of 30 seeds get the correct greedy action in each cell. So, and the green arrow is showing like the relative frequency of each action. So in this top row, it's pretty uninteresting. It's just saying that all the agents succeed. So the color is like basically at 1, and the green arrows are just all pointing along greedy direction essentially. So because they're all basically doing nearly perfectly. Like the one step model failed in I think one seed or something other than that. Okay, so now if we move to the path to goal case, then already DQN fails pretty spectacularly in the bottom 3 cells. And the reason for this is actually pretty intuitive. So the logic is like DQN has only seen what happens if you go right in this specific state from this path to goal data, but it's seen a bunch of data about what happens if you go in different directions from that cell in these kind of basic configurations where there's only one wall. And in those basic configurations, it's actually always better to go up than it is to go right. In particular, like going up is optimal in almost every case, except where there's a wall in this middle cell, so that one spot. And even when there is a wall in the middle cell, going up is still better than going right. Because if it goes up, it's just going to bump into the wall, stay in place, and that's better than moving further away from the goal, which it would be doing if there's only one wall in the way. So it's not really surprising that it's kind of misgeneralizing from these basic configurations in this case to assume that going up is also better in this state it's never seen before. But on the other hand, the one-step model like already is able to succeed here. And the reason is because like all the missing transitions in this state are like one step away from the data. It's just missing the specific actions taken in those states. And the model can actually learn the general dynamics of this environment. Basically, the rule that if I move from a specific cell, take a specific action, I'm either going to move into that other cell if there's no wall in that cell, or if there's a wall in that cell, I'm just going to stay in place. And it's kind of learning that general dynamics information, and it actually does manage to generalize that information to this unseen 2-wall configuration. And we also did verify that it actually was learning the right thing, which is allowing it to basically fill in all these missing transitions, and then DQN is able to learn from those to correct its errors from like the case where we just use the data directly. Okay, so now if we only consider a single cell that's furthest away from the goal, in this case, the one-step model actually also fails. And the reason for that is also pretty intuitive, basically, because it's initialized from states that exist in the data set, and the only state it's seen with 2 walls in the data set is the one that's furthest away from the goal. And we already included all the actions that are available in that state. There's basically nothing for the model to add that isn't already in the data set in this case, so it fails just as badly as DQN here. But on the other hand, the 10-step model is actually able to succeed because it's able to take that initial state, like imagine the next state and the next state after that, and actually fill in all the missing states and all the missing transitions needed to correct the value function in this case. And then last of all, if we include no evaluation data at all, then all 3 approaches fail. And the reason for this is basically they've never seen, because we're initializing the model rollouts from states in the data set, and they've never seen a state with 2 walls in the data set in this case. There's essentially nothing useful the models can contribute that's not already available in the data. This would be different, though, if you were to do something like decision time planning, where we're actually using the model at decision time to figure out what the best thing is to do in this unseen state. But since I don't do that here, it's not surprising that these approaches fail. I'm just like freezing the value function and testing it after. Yes.
So for these training, they're all just pure offline training, and then you just roll them out after that.
Yeah, exactly. It's
So for DQM, why don't we use like offline learning style with batch constrained queue learning?
So I don't remember off the top of my head what batch constrained learning is, but it is like offline learning. I am doing like offline DQN. So I guess how would that change the general picture here?
So I think the general picture is it pretty much deals with like out of support type of
Yeah.
So if there's like say action pairs that you've never seen before, you kind of avoid from
I
taking
see.
these actions.
I don't know if it would be useful to avoid state action pairs here because the agent's kind of trapped in a tiny box. Like there's not a lot I can do if it avoids state action pairs never seen. So, but yeah, I'm not sure exactly how the approach you're describing would affect it. But yeah, I'd be interested to hear more if I want to talk about it.
And the second question is for the single cell setting, why does 10-step help? Like, is it because we're rolling out 10 steps and then it's luckily getting a state where you get a reward of 1 because we know that?
No, so it's basically it's like able to fill in essentially every missing state because if it rolls out 1 step, it now is in this state, right? And then you can just imagine every action. If you do enough rollouts, it'll eventually have like a sample that generates every possible action from this state and then generates the next state and then every possible action from this state, right? So it's basically just able to fill in like not only all the missing transitions, which was able to happen here, but also all the missing states just by doing longer rollouts, right?
I see. And
So-
then and it works because we're assuming access to the reward function.
So here I don't actually assume access to the reward function. I guess I should mention that the reward function is learned here.
But then if you only have a single.
But the reward function is also very simple because it's just it always gets a reward of 1 when it hits the exit. So
But so I guess my question is like in the 10-step rollout version, if your dynamic model doesn't have a reward signal for the goal state, like does it just?
sorry, it does because that generalizes from the basic configuration.
Oh, there's
Yeah, there's still a reward in those configurations. But yeah, good question. That's good to be clarified. I think there's another question, right? Yes.
In the second row, you say that the DQN failed because previously it has seen with only one law.
Yeah.
But with one-step model. So is the model trained on the same data as DQN?
Yeah, the model is trained on the same data as DQN.
Can you explain how does it then?
Yeah, I could agree. I mean, this isn't like a deterministic conclusion. It does depend on how the model generalizes, but basically the idea is that the thing the model learns is that if it's in a particular cell and it takes a particular action and there's no wall in the cell it's trying to enter, then it will move into that cell, right? But if there is a wall in the cell, it'll bump into it and stay in place. And that's something it can learn from these basic configurations, and that does actually generalize to these like 2-wall configurations. So basically the model is able to learn kind of the general dynamics that define this environment. And those dynamics do actually generalize to the 2-wall configuration, which is unlike the way the value function is generalizing. Does that help?
Can you explain how does it generalize when it was trained on the same data?
So I mean, DQN is just trying to learn like a real number associated with each state, right? So so a set of 4 real numbers in this case because there's 4 actions. So basically, like the way it's generalizing is just kind of fundamentally different than the model is generalizing, because the model is generalizing to predict dynamics, and it kind of happens in this case that predicting dynamics, maybe because it's kind of like a denser signal, but anyway, predicting dynamics is kind of easier and generalizes better than predicting just those 4 values. So it's basically like if you're starting in the bottom middle cell, and like I said, if you're learning just from these basic configurations, then almost in every case the best thing to do is to move up. And in this path to goal configuration, it has no data about moving up in the 2-wall state. So it's just generalizing from what is seen in those 1-wall states. And that generalization happens to not work, basically.
And both DQN and models are updated with the online data as well.
Neither of them are updated with any online data, but they both have some data from the evaluation configuration, if that's what you mean.
Well, I meant like when you're interacting in this new grid, do you
Yeah.
update
No, so there's no update that happens. I mean, it's not so much a new world. It's like I'm calling the environment here like every possible layout of walls you could have in a maze, but I'm just including different levels of data about these 2-wall configurations. So both of them are updated on the same data set, which is like all those basic configurations, and then also some data from these 2-wall configurations. So that's true, but neither of them are updated with online data per se, I guess. Yeah. But the model does generate like imagined data and then update DQN on that. So maybe that's what you're getting at. Yeah.
Okay.
Yeah, okay. Sorry, I think maybe that was your underlying question. I didn't get it. Okay. Yeah, I guess I'll keep going in the interest of time. Oh, not a lot of time. Okay, I'll keep going Okay, I'll keep going quickly in the interest of time. So basically we did some extensive RL experiments, tried to keep everything controlled. This is online RL now, so we're not using fixed data sets. The agent's actually generating its own data. And basically, yeah, we're controlling as much as we can between the model-free and model-based methods. And 3 different environments, they're kind of designed to have this property that there's something in the environment that a model can kind of learn that generalizes to unseen states. So lots of states, but the model has some ability to generalize in each of these. And then here's the results. Essentially, we compare experience replay, learn model, perfect model. And the general picture is that as we increase the environment complexity, so the x-axis here is like some measure of environment complexity. So in this proc maze case, it's, for example, the size of the grid world maze we're looking at here. And these are like randomly generated mazes in this case. What we see is that as we increase the environment complexity, there's some point where the experience replay alone starts to fail quite dramatically generally, and the learn model continues working for some period of time after that. And we also include a perfect model for comparison, which is like the same algorithm, but the agent doesn't have to learn the model anymore. And yeah, one last interesting thing here, in this pan-fluid environment, we actually saw the learned model outperform the perfect model. It's kind of orthogonal to the focus of this talk, but we actually do have a pretty good idea of why that was. So you can see the paper for details if you're interested, but yeah, that's not explainable by anything I've talked about so far. And then the last thing I want to mention is that if we run a learned model in a state where there's like an unstructured environment, this thing is actually inverted. So this is kind of illustrating this point that there has to be something for the model to actually be able to generalize from. This grid, this is basically just like a tabular grid world where every state action pair is kind of independent. So in this case, the model can only basically memorize transitions, and experience replay is always going to do a better job of memorizing transitions. So in this case, it actually performs better instead of worse as we increase the complexity. So yeah, just there has to be some kind of generalization for this to work. So key takeaways, intuition that model-based learning should be more sample efficient is well justified. In complex tasks with some underlying learnable structure, a model-free approach can lose value-relevant information from the data that analogous model-based approach can capitalize on. And this is true even when the model-free and model-based approach begin with the same prior knowledge of environment structure. And empirically, we find it's true in environments with factored structure, even when using simple feed-forward neural networks for function approximation. Okay, that's it. So now there's.
Thank you so much for your presentation.
Yep.
Anyone who needs to run can go ahead, and anyone who wants to stay and ask more questions, we're down for that too.
Yes.
So based on the conclusions, do you have a statement that you would like to you started with a question of there's a body of work questioning whether models should be accurate or should they be just be useful. So do you have something to say to that?
That actually plays in pretty well to like what was going on here. So this is an inaccurate model was actually more useful than the true model. And that's kind of independent of the main conclusion I'm trying to talk about in this paper, but it's independently interesting, I think. And I don't have like a good global answer to that question. But in this specific case, the reason the learned model was better than the true model is because it was doing some kind of like smoothing sort of. So it was giving the agent like a smoother reward signal to learn from because it was inaccurate, and that was actually helping with exploration, which probably wouldn't always, but maybe in like reasonable problems, that's a real effect. I don't know. I think that'll be worth looking into more. Yeah. Yes, wrote that. Oh, sorry.
Sorry, just so then outside of that, is it, would you have something to say to that body of work? Like
I mean, I think models. Okay, so if you just fit your model based on like being able to predict value functions, I think that's inherently limiting because you're always going to have missing information. So it might be good to use some kind of like auxiliary reward signals to learn your model, but also like limited model capacity is a real thing. So maybe the right thing to do is like learn as much as we can, but if we can't learn everything, bias it towards things that are actually value relevant. If that helps. Yeah. So some intermediate is probably the answer, I think.
So, going back to the theory section about like, so you're talking about how the tabular setting like this benefit doesn't go.
Yeah.
But the counter example you gave is tabular, right? So what's going on?
No, it's not quite tabular. Let me go back to it. Yeah, so this was the counter example. So yeah, in what sense is this not tabular? It's basically not tabular because if you see a particular like response to a particular passcode, that tells you something about the responses you're going to get to other passcodes. So tabular would be like you just see that particular response that only tells you something about that specific transition, right? So, but I guess I should emphasize what I mean by tabular. I just mean like the model class considers every possible like state action to next state tuple equally likely. So anything that breaks that is a valid way to.
So the model class is factored, like you were saying. So,
Yeah.
So seeing a transition in one state never tells you anything about a transition matrix. That's what you meant by that.
Yeah, that's what I meant by tabular. Yeah.
So the model class cannot have like long range dependencies, right? In the sense that like yeah, exactly what I was saying. So you can't have an equation where going one state.
Yeah, exactly. Sorry. Yeah, like it can't have dependencies between. Yeah, I guess long range dependencies is one way to explain that. Yeah. Yeah, I meant tabular in like a fairly strict sense, I guess. So could have emphasized that.
And is there like an analogous definition for Q functions? Like, what would it mean to say that a Q function does not have long form? Or a class of.
Well, you could just consider like the, oh, I mean, that's a good question, because like you would have to bring in the reward as well in that case. I mean, if you fix the reward function, then I guess you could just call it the Q functions of the tabular models, and that makes things easy. But I'm not sure what the definition would look like beyond that. Like if you had like sort of an arbitrary reward or a reward between 0 and 1 or something like that. Like, yeah, I guess this is like sort of a fairly simple setting that I'm hoping can bolster some intuition, but there's a lot to be said about for sure more complicated settings.
I really like this starter example, which is why my brain's just like trying to dig into it.
I see, yeah.
What is actually happening here?
Yeah, I should mention that this is actually not my counterexample. I had a worse one, but then I found this one in another paper. So since you're praising it, I probably shouldn't just take the praise. So from when Sun et al. So if you want to look at another great paper on sort of this model-based model-free question, then yeah, have a look at that.
And if we would go to the trinary tree here, the last node would still only have like a 0 or 1 saying if the action is correct or not, right? Or would you go to 0, 1, 2 then?
Yeah, I mean, you could do either, right? I guess if you had the 0, 1 indicating whether it's correct or not, that would be a more limited feedback.
Yeah.
And in that case, but it wouldn't tell you nothing unless it wouldn't tell you nothing. It would still tell you something, right? If you got any digit right, that would still be more informative. Even if you didn't get the reward, you still get more information than the model free agent had access to.
Yeah.
So it wouldn't totally break the example, I don't think, but it would definitely change things. Yeah. Yes.
So I was wondering, have you ever thought of, or are there any words that kind of like describe this structure of the environment?
Sorry,
you can use more formal language to describe what kind of environments model-based.
Oh, yeah, I think that's something that this When Sun paper digs into a little bit. I'm not exactly sure how much, but they have sort of like, I forget what the exact name they call it, but they have some sort of like feature relating to the environment or some like, what's the right word for it? Like some property of the environment that kind of describes how well their model-based algorithms will perform versus how well their model-free algorithms will perform. So I think, yeah, there's a little bit of that in this paper, but I'm not sure how extensive it is. Hey, maybe interesting to look at. Yeah, is there anything else? No? Okay.
All right, great.
Thanks, everybody.